I guess let's get started and let's talk a little bit more about the problem we're solving. We are helping clinicians better analyze medical images to optimize the reporting workflow, cut down some of the time that it takes them to report on medical scans, increase the accuracy of the reports. And at the same time, we're trying to give them advanced risk factors out of these medical images in order to help them better predict and prevent a stroke. So let's talk about a stroke for a second. It's very similar to heart attacks and one of the biggest killers in the world. Depending on which country you live in, it's typically in the top 3 causes of death. It affects more than 15 million people every year. And unfortunately, more than half of those people end up either dead or disabled. And there is another sad statistics there that quite a lot of stroke patients are in risk of recurrent strokes. And these recurrent events are even more deadly with higher risks of disability for the patients. Among all of these, sad news, there is a piece of great news, which is if we can predict a stroke, we can do something about it and we can prevent it. And this is exactly the type of problem that we're trying to solve. Let's dig in a little bit more into the management method for stroke patients and see where exactly is the problem. So strokes happen, as a very quick, like a stroke 101, strokes happen because of blockages in blood vessels, either in the neck or in the brain, that cut blood flow to the brain, and that cuts oxygen to the brain, causing cell damage, and that's essentially the cause of that death and disability that I mentioned. So these blockages, a lot of times, are caused by plaques of fat that build up over time in the blood vessels. It's a lifestyle disease, as I mentioned, very similar to heart attacks that are caused by coronary artery disease. So these plaques of fat build up in the blood vessels, and the majority of strokes happen because of these. In the current workflow, clinicians take a lot of medical images from patients that are in risk of a stroke. So either patients that have had a stroke before, or patients, for example, that have had a history of heart disease and are getting scanned for a stroke. Clinicians would essentially take a lot of either CT scans as the first line of defense, and then ultrasound and MRI images from these patients. And they would look at the degree of narrowing in the blood vessels. So if this plaque of fat is restricting the blood vessel, they would measure the degree of narrowing. And if it's, for example, more than 70% narrowed, they would do surgery for the patient. But unfortunately, this is not adequate, especially based on latest clinical evidence published over the past 10 years. We know that it's much more important to know what is the composition of the plaque and how it interacts with blood vessels, how it interacts with the blood flow in the blood vessels, essentially. So that plaque composition and high-risk blood flow pattern, those are the 2 most important risk factors to come up with a good prognostication, a good treatment plan for the patients, but that's missing from the current clinical tools. And that's exactly the crux of the problem that we're trying to solve. But before we get to those advanced risk factors, before we get to those plaque composition and blood flow analysis, we actually discovered that there is another problem that clinicians face, which is just reporting the images that they currently take is a highly time-consuming, highly manual and error-prone task. So they would look at images one by one, scrolling through hundreds of images at times, and then manually they start writing down reports based on those, transcribing numbers and measurements. And naturally, that becomes quite an operator-dependent and error-prone process. So we broke down the the moonshot mission and vision of the company into essentially these 2 different groups of products. The first products that we're building and is currently commercial, it's all about image interpretation and reporting. And our future products are helping clinicians get advanced risk factors for stroke prediction out of these images. So let's talk about that product roadmap in a little bit more detail. Our first product, which I mentioned is currently in the market, it's called AVA, short for Augmented Vascular Analysis. Or if you're Iranian like me, it's called AVA. And it is a clinical tool that helps clinicians streamline their reporting workflow for ultrasound images. It speeds up the process of reporting these scans for them. And then we're building on that our future products, Plaque, which analyzes plaques in CT scans and ultrasound images, and then Flow, which detects high-risk blood flow in CTs and MRIs. So while our first product is currently commercial and in the market, our future products, Plaque and Flow, are currently in development. So I guess let's dive in to a quick demo of our first product and see what is exactly the problem we're solving. And I'll try to touch on some of the utilities of machine learning in solving this problem, because I think, as we've spoken to a lot of clinicians, they wanted to solve this problem like 10, 15 years ago, but the tools were really not there. So machine learning here has really become an enabler for us to be able to bring this into market. So let's dive in and take a quick look at the problem in a little bit more detailed, and then I'll share the demo with you. By the way, Rahim, if you're still with me, can you confirm that you can now see a scanned piece of paper on the screen? Hope that's come up, or any of the moderators.
Don't you hear me?
So you should be able to see a different screen now, a scanned piece of paper.
Yes, we are able. Yes, we are able to see this.
Awesome, lovely. Thank you, Ryan. So this is a scanned vascular ultrasound worksheet. So this is currently what happens when a patient goes to a hospital and is going to be imaged for stroke management. A sonographer would take an ultrasound probe, similar to how they scan for pregnancy and babies. They would move that probe across the blood vessels in the neck, and they would take a lot of images from the patient, 50 or 100 images. And then they start going through those images one by one. And on a computer, they look at those images, and then they've got this piece of paper in front of them, and they start drawing in what they've seen in the images. So they would, for example, draw in that I saw a 50% narrowing of the carotid artery bifurcation, for example. Or these are the numbers and measurements from blood velocities that I measured across the blood vessels here. As you can imagine, this is a highly time-consuming process, especially if it's a complex patient, just to transcribe all of this data from the images into the report, let alone interpreting the images. And it's of course highly error-prone. So we've seen in some of the examples of worksheets that we've analyzed from different centers that a sonographer has correctly acquired an image from the blood vessel, for example, an occlusion, a full blockage of the blood vessel, which could be quite devastating. They've correctly imaged it, but they've reported it in the wrong artery, for example, in the wrong side. And these are exactly the type of errors that we're trying to prevent. So now that we've talked a little bit more about the problem, let's dive in and take a look at the solution and how machine learning here is coming in to play. So if you give me a second, you should be able to see my screen now. And sorry, Raim, just help me out for one more second, making sure my share screen is working okay. You should now be able to see a live demo of our application, the C-Mode app on top. Is that working all right?
Yes, we see the app.
All right, awesome. So let's dive in and take a look at a live demo. So you saw those paper worksheets, and as I mentioned, that takes a long time for a clinician to build, and it could be quite error-prone. So here I've logged in as Milad, the sonographer, and I've got 2 studies in my work list of studies that I could report. So these are the same type of images that a clinician would take in their routine workflow. We don't change anything about the workflow that they take those images with. And when they log in, they would essentially have access to their images that are analyzed automatically by the computer right as they've left the ultrasound room. So essentially those images go from the ultrasound machine to a database of images in the hospital called the PACS system. From that PACS system to our AWS server, they get analyzed. We create a report for the clinician. And the moment that they log in, they would start seeing essentially a report that's fully built for them. So on the right-hand side of the screen now, you should be able to see a fully completed worksheet based on these images that are now on the left-hand side. So all of the images that the clinician has captured, we've included them here. And for example, this outline that you see, this green outline that you see, I'm toggling on and off on these images, that's created by a segmentation model, a deep learning model that we're using to segment the arterial walls essentially here and detecting any plaques that could be creating a risk of stroke for the patient. Now that alone is a juicy computer vision problem to solve using machine learning, and it comes with its own complexities. So a lot of times, for example, you have a part of this blood vessel that's fully dark and it's not actually visible in the image because of noise and artifacts that are associated with ultrasound imaging, especially calcification. It's causing acoustic shadowing, for example, on the outer wall of the artery. And this was a pretty complex computer vision challenge that our team had to work on, essentially creating their own GANs that we started calling anatomical GANs that learned to essentially connect the dots. And if there was acoustic shadowing or if there was a missing piece of the image, it learned on how it should connect the missing pieces in that image together. So we've essentially looked at the images. We've created drawings for the clinician based on those images, fully completing the worksheet for them. Not just that, we're using, for example, text recognition, again, based on machine learning models to be able to detect any annotations they put on their images and learn that this image, for example, is captured from a specific body part before completing the worksheet that is generated based on that image. Or running some classification problems. For example, our machine learning models here have detected that this indicates a fully occluded blood vessel using a classification problem, essentially. Is this an occlusion or not? And they've detected that, yes, this indicates an occlusion, and we've represented corresponding occlusions here for the patient. So using a combination of segmentation, classification models, solving different problems in addition to text recognition, we're able to put together this worksheet for the clinician. But as I mentioned, I'm no machine learning expert, but I want to essentially emphasize on two important things here. One is that the advancements in machine learning really have enabled us, as well as other companies, to be able to solve these type of cool problems for the clinicians. If they wanted to solve this 10, 15 years ago using traditional computer vision techniques, edge detection and whatnot, it would not have worked in almost all cases. Or in very simple cases that are just healthy, it might have worked. But now with machine learning, we can actually take that to the next level and look at detection of complex pathologies for these patients. That's one. The other thing that might be interesting for you all to know is that building the machine learning model, believe it or not here, is not the hardest part of solving this problem for the clinicians. One of the hardest parts of solving this problem for them is actually the user interface and experience that we had to create. So this is not images that are taken. This is essentially not a result that's coming from one image. This result is coming from around 20, 30 images from each side of the patient. And we've got a similar type of story on the left-hand side as well. So how do you enable the clinician to be able to quickly review the results that are generated by the machine learning models, verify that those results are accurate, and then give them the ability to change those results if it's appropriate? So that was a pretty complex user interface and experience challenge that we had to solve. So coming back and just wrapping up with a couple of insights into the future products that we're building. So with our first product, as I showed you, we really tried to solve that problem of image interpretation and reporting for the clinician, putting together a worksheet that's as accurate as what they currently put together, but in a much shorter amount of time. With our future products like plaque and flow, what we're looking at is essentially detecting high-risk plaques or detecting risk factors of a stroke, but based on the images. And here you're looking at a classification problem that we're solving in order to do that. So on the left-hand side, you've got an image of a plaque that essentially has blood inside it. It's called intraplaque hemorrhage, or IPH, which can create a high risk of recurrent stroke for this patient. On the right-hand side, you've got a plaque that does not have blood inside it. It could, for example, have a higher percentage of calcium or fat inside the plaque, but not as much blood. And this does not create as much risk for the patient to have a recurrent event. Now, if a clinician looks at these two and tries to make a guess, a judgment call, they would be correct just over 60% of the time. And this is not a high accuracy for them. This is, especially looking at their sensitivities, less than a coin toss. And that's why they currently do not make that judgment call. But what we managed to do in a clinical study that we ran with National University Hospital in Singapore, and now with Oxford University Hospital in the UK, as well as Royal Melbourne here, as well as Austin here, what we've managed to do is to train a machine learning model that can detect these high-risk plaques with high accuracy. So for example, in classification of IPH, we reached around 90% accuracy, which is a significant leap compared to what the clinician can make now. And again, I think this is a good place to emphasize on the fact that these type of problems are really enabled by machine learning now. These type of solutions are really enabled by machine learning now. And the levels of performance here that we're seeing is much higher compared to the papers that have looked at solving similar problems, say 10 years ago. And what we're trying to do now is to essentially validate this with as much data from as many different hospitals as possible. And I think a good place for me to end now and just open it up for you all for questions is just talking about some of the challenges of solving these type of problems using machine learning. So one of the interesting challenges, especially when it comes to detection of high-risk plaques, for example, is that your ground truth, your label, cannot come from the clinician. They wouldn't make the correct judgment call. So how do you know which of the plaques actually has which composition? So for that, we had to use high-resolution MRIs, which are research modality, very expensive, only available from within specialized research centers. And that highlights really that problem of lack of high quality data, especially for some more complex clinical problems that you're trying to solve. So I don't know, if you're trying to detect pneumonia in chest x-rays now, there are millions of images that are available and a lot of public data sets. But if you're trying to solve some more niche, specialized type of clinical problems, you really have to come up with methods that you can use a small amount of data in order to generate your models and validate them. And you need to be super careful about, making sure that your methods for, splitting the data set, k-fold cross-validation, these methods are generating models that can, when they go into production, they can essentially generalize based on the data that they see coming. So that's one of the problems that's pretty interesting here. And another one is the abundance of noisy labels when it comes to medical imaging. So you're seeing here that, for example, if we have got two experts making guesses here, their guesses could be different. Here, we're not using the expert's judgment call in order to determine the type of the label that we should essentially assign to each of these images. But for some of the problems, we have to rely on expert annotations. And especially when it comes to ultrasound as a modality, you would have a lot of problems that you've got, for example, 3 experts, and each of the 3 is annotating the image differently. It's essentially having a different label associated with the same image. And now try to build a classifier where your 3 experts actually do not agree on what label that image should have, right? So I'm exaggerating here to make a point. In a lot of the cases, we can at least get a majority votes between the experts. But this is, again, one of those exciting challenges, I think, of applying machine learning in the clinical setting. just dealing with these noisy labels and coming up with clever strategies on how you handle that in your machine learning model development process. A really good example that comes to my mind now is that we're now trying to expand our first product to other ultrasound use cases outside of the vascular domain. And one of those problems we're trying to solve is for thyroid nodules, for essentially thyroid cancer. And we had to come up with methods that can essentially look at labels associated with the same image by, say, 3 sonographers, choose the majority vote, and then use that, for example, as the label associated with the image in the training process. But when it comes to the validation process, we can use a minority vote, or at least if our model agrees with one of the 3 experts, that should be that could be a good model. At least it's not giving something that none of the experts said. So these are some of the, again, like some of the exciting challenges of applying machine learning in that clinical setting.